Let's look at this table and see how the signs of the first and second derivatives work together. Case 1. If the first derivative is positive, the function is increasing. If the second derivative is positive, the graph is concave up. So in this case, the function is increasing and concave up. And it looks like this. Moving on to the second case. The function is still increasing because f prime is positive, but now the second derivative is negative, so the graph is concave down. The third case, now the function is decreasing because the first derivative is negative, but the second derivative is positive, so the graph is concave up. In the last case, the function is decreasing and the graph is concave down. Now, let's look at this graph to see how all of this appears visually. As we move from left to right, notice how behavior changes in different regions. Each region is separated by these vertical dashed lines. The first region, the function is decreasing and opens upward. So f prime is negative and f double prime is positive. Second region, the function still opens upward and increasing. So f prime is positive and f double prime is also positive. Third region, the function is increasing and opens downward. So f prime is positive and f double prime is negative. The fourth region, the function is decreasing and opens downward. So f prime is negative and f double prime is also negative. So this graph shows how the first derivative controls direction and the second derivative controls shape. Now, let's introduce a faster way to classify extrema. Instead of using a full sign chart every time, we can use the second derivative test. Suppose f prime of c equals 0 and f double prime is continuous. Then, if f double prime of c is positive, the graph is concave up, so we have a local minimum at c. If f double prime of c is negative, the graph is concave down, so we have a local maximum at c. If f double prime of c is 0, then the test is inconclusive. So now we have two ways to find extrema. The first derivative test uses sign changes, and the second derivative test uses concavity. Now that we understand the second derivative test, let's organize it into a clear step-by-step process. Step 1. Find the first derivative, f prime of x. Step 2. Set f prime equals 0 and solve for x. These give us the critical points. Step 3. Find the second derivative, f double prime of x. Step 4. Evaluate f double prime of c. This means we want to find the function values at each critical point we found in step 2. And step 5. If f double prime of c is greater than 0, then the function has a local minimum at c. If f double prime of c is negative, then the function has a local maximum at c. And if f double prime of c equals 0, then the test is inconclusive. When the test is inconclusive, you need to use another method. Now, let's apply these steps to an example. We're given the function f of x equals x to the fifth minus 5x to the third. We want to use the second derivative test to find all local extrema. Step 1, we need to find the first derivative. F of x equals x to the fifth minus 5x to the third. F prime of x equals 5x to the fourth minus 15x squared. Step 2, we set the first derivative equal to 0 and solve for x. So we have 5x to the fourth minus 15x squared equals 0. From here, we'll factor out 5x squared times x squared minus 3 equals 0. And we set 5x squared equal to 0 and x squared minus 3 equal to 0. To solve for x from this equation, I'll first divide both sides by 5. So I have x squared equals 0. Then I take square root of both sides. So I have x equals 0. To solve for x from this equation, I first add 3 to both sides. So I have x squared equals 3. Then I take the square root of both sides. Now, when you take the square root of both sides of an equation, do not forget the plus or minus. I did not include plus or minus here because plus or minus 0 is 0. But for a non-zero number, always remember the plus or minus. So x is plus or minus root 3. So I have three critical numbers, x equals 0, root 3, and negative root 3. Step 3, we need to find the second derivative. To find f double prime, we'll differentiate f prime. So we have 20x to the third minus 30x. Step 4, we want to evaluate f double prime at each of the critical numbers. So this is f double prime, and I want to find the value of this function at 0, at root 3, and at negative root 3. At x equals 0, f double prime of 0 equals 20 times 0 to the third minus 30 times 0, which is 0. What does it mean when f double prime of 0 equals 0? Go back to the second derivative test. If f double prime of c equals 0, then the test is inconclusive. That means we don't know if C is local min or local max. Now let's find the value of f double prime at x equals root 3. When x equals root 3, f double prime of root 3 is 20 times root 3 to the third power minus 30 times root 3. And from the calculator, I get 51.96. Now, the reason why I convert that into a decimal here, even the question doesn't ask for approximation, because I just want to know if this number is positive or negative. So 51.96 is positive. What does that mean? When f double prime of C is positive, then we have a local minimum at C. That means we have a local minimum at root 3. And then we do the same thing for negative root 3. We want to find f double prime of negative root 3, which is 20 times negative root 3 to the third minus 30 times negative root 3. And I get negative 51.96. So f double prime of negative root 3 is negative. What does that mean? So go back to the test. If f double prime of C is negative, then there is a local maximum at C. So we have a local maximum at x equals negative root 3. So we have three critical numbers. At root 3, we have local minimum. At negative root 3, we have local maximum. At 0, the test is inconclusive. That means we don't know if there is a local minimum or local maximum at x equals 0. So when you use the second derivative test and it's inconclusive, we have to use another method. So let's continue using another method for x equals 0. Since the second derivative test is inconclusive at x equals 0, so we will use the first derivative test to determine what happens at this point. So let's recall the first derivative. F prime of x equals 5x squared times x squared minus 3. And now I check the sign of f prime around x equals 0. Let's create a number line. Notice that I include all three of the critical numbers in this number line. But I will not check the signs around negative root 3 and around root 3 because I already classified them using the second derivative test. So I only need to check the signs around 0. Now I want to know if f prime is positive or negative here, and if f prime is positive or negative here. So let's pick a number in this region. Say I pick negative 1. Negative 1 squared is 1, and 1 times 5 is positive. Negative 1 squared is positive 1, minus 3 is negative. Negative times positive is negative. Next, let's pick a value in this interval. Let's pick 1. 1 squared is 1, times 5 is positive. 1 squared is 1, minus 3 is negative. Negative times positive is negative. So the function is decreasing in this interval and also decreasing in this interval. Since the function is decreasing on both sides of x equals 0, there's no sign change. So x is not a local maximum or local minimum. This is just a point with a horizontal tangent, but not an extremum. So we have a local minimum at x equals root 3 and a local maximum at x equals negative root 3. The question asks for the location of the local extrema. That means we have to find both x and y coordinates of the local extrema. So we have a local minimum at x equals root 3. To find the y value, we just plug root 3 into the function f of x. So the local minimum is at root 3 comma f of root 3. Now we need to find f of root 3. F of x equals x to the fifth minus 5x to the third. F of root 3 equals root 3 to the fifth minus 5 times root 3 to the third. From here, I factor root 3 to the third out, and I have root 3 squared minus 5. Root 3 to the third is 3 root 3. Root 3 squared is 3. 3 minus 5 is negative 2. And negative 2 times 3 is negative 6. So I have negative 6 root 3. So the local minimum is at root 3 comma negative 6 root 3. Next, let's find the location of the local maximum. Local maximum is at x equals negative root 3. To find the y coordinate, I plug negative root 3 into the function f of x. So I have f of negative root 3. Okay, so I want to find f of negative root 3. From here, I factor out negative root 3 to the third power. So I have negative root 3 to the third times root 3 squared minus 5. Negative root 3 to the third is negative 3 times root 3. Root 3 squared is 3. 3 minus 5 is negative 2. And negative 2 times negative 3 is positive 6. So I have positive 6 root 3. So the local maximum is at negative root 3 comma 6 root 3. Notice that I didn't turn these numbers into decimals because the question does not ask for it. In general, we should always give exact answers unless a decimal is requested.